Okay, and let's switch to full view. Let's have a look at the agenda. So yesterday we talked about the basics behind the main ideas behind the aeroacoustics, and then we switched to direct computational aeroacoustics. Today we are going to talk about acoustic analogy and a more dedicated model related to acoustic analogy. And you have two workshops to do on this topic because it's a very important model within ansys, so you have two workshops dedicated to this topic. Okay, so let's go now through the presentation. Okay, so the acoustic analogy. So we'll see some principles, some ideas behind the acoustic analogy, the main ideas, the main motivation behind this acoustic analogy idea. I like this equation and Green's function. Green's function is important to derive, in fact, the acoustic analogy and use it and implement it in ansys. Then we will talk about curves and even more important, Fox, Williams and Hawkins formulations that are used in fact in ansys. And we will talk about also the strengths and limitations of the acoustic analogy, because you will see that there are some limitations to this approach. And you need to be aware of this limitation before using this model for aeroacoustics. The implementation of the Fox-Williams and Hawkins equation within ansys, we'll see some details about that, and accordingly the main steps for calculating and post-processing the results, because you will see that you have different information from a classical CFD calculation. You have a dedicated results to aeroacoustics, and you have to do some specific treatment to extract this information, this acoustic information, from your calculation. And then we'll go through some case studies with the Fox, Williams and Hawkins approach. Okay, so let's start. If you remember, on first session, I was talking about acoustic pressure, acoustic density, acoustic pressure, acoustic energy. All these quantities, if you remember, I was telling you that these quantities are very far in terms of values compared to the standard aerodynamic quantities. And we need to be extremely careful when we manipulate these acoustic quantities, because they are kind of different from the usual quantity that we have in an aerodynamic equation. And in fact, when we are talking about acoustic pressure fluctuation, we are talking about quantities that are extremely small compared to the aerodynamic pressure fluctuations. So here you have some figures that illustrate this point regarding a certain kind of acoustic information. For some pressure level of 60, 100 and 140, you have different levels of root mean square of pressure, of acoustic pressure. And the important point here is to recognize, to acknowledge that this value for the acoustic pressure is quite small, very, very small. You see you have something around 1.02 Pascal, 2 Pascal or 200 Pascal. Even 200 Pascal is not so high compared to the atmospheric pressure, which is 10 to the power 5 Pascal. So it's quite far from this atmospheric pressure. And at this point, one important thing is that when you use classical CFD methods, and the numerics behind these classical CFD methods, they are usually designed, they usually try to damp spurious oscillations. And when they see some oscillations, such as an acoustic wave, a classical treatment would be to damp this fluctuation, because it's something which is usually created by the numerics and want to get rid of it because it's not important, it's not the aerodynamics. But problem here is that this acoustic information, we want to keep it. It's not a good idea to damp it. We want to keep it because it's exactly the aeroacoustic data we want to recover from our calculation. So main idea would be here to decouple acoustic from flow dynamics. And the idea is very appealing. Why? Because we know that acoustics is involving quantities that are far below in terms of values compared to flow dynamics. If you have a look at the acoustic pressure, it's quite clear. So another point to go into that way of separating in fact aeroacoustics from aerodynamics is if you consider in fact the trend of evolution for the pressure. If you consider the aerodynamic pressure and the acoustic pressure, they do not evolve in the same trends. For aerodynamics, the pressure will decay when you get further away from the obstacle that is creating, for example, your turbulence. The pressure that is created from all these eddies, it will decay in a trend which is 1 over R, or the distance from the source of the vortices, the turbulence source, R to the power 3. Cube R to cube R. And for aeroacoustics, you have only a decay with a trend of 1 over R. So it's a much slower decay. That means that you will keep some information from aeroacoustics, even if you don't have any more information, sensible information from aerodynamics. So you need to be extremely careful. But this difference in terms of decay, in terms of trend of evolution for aerodynamics and aeroacoustics, also goes in the idea, towards the idea of separating aerodynamics from aeroacoustics. So if we get back to the constitutive equation of aeroacoustics, if you remember, I presented these equations on session 1. Start from mass, start from momentum equations, conservation equations. You do some kind of treatment, deriving these two equations, and then you obtain, you have the formula here used, and then you obtain, after getting rid of certain terms, you obtain the wave equation. And in this wave equation you have 2 left-hand side terms and 1 right-hand side term. And the right-hand side term is quite important. It's in fact the term that is making the difference between the homogeneous wave equation and the Navier-Stokes equation. So in this term, you have everything that is coming from the Navier-Stokes equation. So it's a very complicated term. It's called the Leibniz tensor. In the Leibniz tensor, you have everything that is not exactly the homogeneous wave equation. So we separate the homogeneous wave equation term, the left-hand side term, that represents in fact the wave contribution, from the rest that comes from the Navier-Stokes equation. That means that the Leibniz equation, so this equation, Leibniz equation, is formally exact. It's in fact the same complexity as the Navier-Stokes equation. You don't have any approximation at this point. So it's quite complicated. That means that this Leibniz equation is no easier to solve than the original Navier-Stokes equation. At this level, it's clearly a problem. So what are we going to do at this point? The acoustic analogy idea by Leibniz is to separate, to consider different kind of equations based on the regions we are going to consider. So for example, here you have a jet which is emerging in an atmosphere, a plenum, for example, a very large plenum, and then we are going to separate regions. The idea is to separate a region where you have the jet, which is a source of acoustics. We have all the complexity, so we are going to consider the Navier-Stokes equation and correspondingly the Leibniz equation. So we are going to consider this equation, and further away at some frontier around this acoustic source, we are going to set some frontiers, and from these frontiers we are going to define other domains, and in these domains we are going to make some simplification. That is, we are going to consider homogeneous wave equation in a uniform stagnant medium that is only propagating the acoustic information. So we separate the domain to 2 different kinds of contribution. A source region, where we are going to consider the whole complexity of the creation of turbulence and then acoustic information, and external regions, where we are going to transport all this complexity in a stagnant, uniform quiescent medium, in fact, with these properties which are set, which are not evolving. So we are going to simplify drastically the problem. We are defining a complex region and some transporting region that will transport the information that we hope is quite accurate in the source region. So the idea of the acoustic analogy, the Leibniz acoustic analogy, is to separate, to consider different domains and to transport the acoustic information with different kinds of equations. a complex equation inside the source region and a simplified equation outside. So based on this latest acoustic analogy, we have main ideas. Main ideas are noise sources are assumed to be set in a uniform fluid at rest, a quiescent fluid in fact, with uniform properties. We are going to define the acoustic field at the receiver by the homogeneous wave equation. We are going to use the homogeneous wave equation. So we don't have any right answer. We completely forget the lattice tensor at this point. And we are going to decouple acoustics, aeroacoustics, from aerodynamics. So it's completely separate problems at this step. So more practically, when you do your calculation, you will first simulate the CFD solution, the classical CFD solution with aerodynamics. And since you are sufficiently fine in terms of spatial and temporalization, you understand at this point that you will also consider aeroacoustic sources inside this region. So you will solve both aerodynamics and aeroacoustic contribution inside the source region. So that is the first step. And the second step is that at the frontier, that are the borders of your acoustic source, you will propagate the noise from these frontiers up to the receiver, and you will solve a wave equation analytically, so that will be a much simpler calculation compared to classical CFD calculation. So the main point here is to say, at this point, at the frontiers of my source, I have all the information I request to solve the aeroacoustics, and then to propagate the further this information, I will only solve an analytical equation. And that is the main strength behind this idea. So if we take a look at this small image here, at the bottom of the slide, we have a CFD domain. For example, you have a cylinder. In the wake of the cylinder, you know that you will create some eddies. These eddies will contribute, so you take into control these eddies plus the walls of the cylinder. That is your source region. You have some frontiers, some borders of this source region, and from the borders, you transport with a wave equation, and you solve analytically this transport of acoustic information up to the receiver, acoustic receiver. Okay. So at this point, one important idea is to say, okay, yes, now we know that we are going to separate all the regions, but how we do that? How can we formally solve this problem? So at this moment, it's nice to have a look at a very simple source of sound, which is a Dirac source of sound. That is a source of sound which is extremely localized and extremely short in time. So something which is nearly a point in both space and time. So for example, you have a gunshot. The source of emission of the sound is quite small, it's the mouth of the gun, and the sound is quite short in time, because the gunshot is very short, correspond to a sound which is emitted on a very short duration. So this a good image to represent this kind of sound that we are going to study here. So at this point, we consider the wave equation, and on the left, the right hand side, the emitter, the type of emitter, is a Dirac function. Dirac function both in space and time. And the solution to this equation is well known. In fact, it's a Green's function. And the Green's function is written that way. So we have a dependency 1 over r. It's nice when you see that, you immediately remember that I was talking about a decay with 1 over r for the aeroacoustics, and we recover this decay with a Green's function. So it's very nice at this point, because we know at this point that we have the correct decay trend for this from this Green's function. So the solution, it represents spherical waves that arrive at the receiver with a certain delay, which is related to, in fact, the propagation speed of the acoustic wave and the distance from the receiver, from the source, which is very localized, up to the receiver. And the decay is quite nice, as we saw earlier. So now we know that we have a solution, and we know how to write this solution for a very simple source. So now that we know this solution for this very simple source, all we have to do is to make a product of convolution between this source and the 3D Green's function, because we can combine any source with this Green's function to obtain, in fact, the response for any kind of source. And this is exactly what is done here. So you recognize, in fact, some contribution from the Green function, and S is your source. It can be of any form. And if you do a compact source approximation, that is, you consider that the distance from the receiver to the source is not changing that much. In fact, that the source is quite compact, and that all points that emit a sound are nearly at the same distance from the receiver, you obtain this kind of solution. We are not going to use this approximation in ansys Fluent. We are going to consider certain localization of the sound sources. So it's not this kind of approximation that we are going to use. But you can obtain, if you want to apply a compact source approximation, you can obtain a very simple representation of your sound source. So, okay. Nice. At this point, we know that we have some way to obtain, in fact, this solution. And why not applying this solution to the lighted stancer? Because, in fact, it's a lighted stancer that has everything in terms of information for the acoustics that we want to solve from our CFD flow field. So idea at this point is to say, okay, I have the Green function, I have the lighted stancer, I will convolute these two terms. So that is what is done here, and I will obtain this kind of representation of the solution of the wave equation for typically these sound sources. So this solution represents the propagation of the sound which is generated by the fluid motion in a free space. So that is, at this point, you don't have any walls or any obstacle to the sound sources. It's exactly the same for the gunshot. When you have the gunshot, you don't have any obstacle between the source, the gun mouse, the source of sound, up to you. You don't have any obstacle. This clearly, in this analogy, this is clearly the propagation of an acoustic wave which is generated at a certain point in space. And this propagation is not hindered by any obstacle or walls. You don't have any reflection at this point. So, okay, this is the first option, the lighted tensor to take into account. But what if we have some walls? We want to include the effect of walls. So the idea of curls in so some years after lighting in 1955 was to add certain contribution, which is a surface contribution, which correspond to walls inside the sources. So the main idea is to separate, in fact, a volume integral and a surface integral. So here we are going to consider noise generated inside the fluid volume, which corresponds to quadruple sources, and we are going to add another term which corresponds to sound emitted at the walls. So we are going to consider two kinds of sources: quadruple sources emitted from inside, it's a volumic contribution, and noise sources that are emitted from walls. In fact, it's a surface contribution. So that's why you have an integral over surfaces inside the source region. It's a dipole source. And to go even further, Fox, Williams, and Hawkins derived a more generalized Lattier equation which is valid for moving surfaces, because in curves formulation you are not taking into account moving walls. So what is the idea for Fox, Williams, and Hawkins? To add a contribution, another contribution, to take into account moving walls. And to do this, they will include this function f, which is a marker of the source, but also a marker of the domain external to the source. So this is very nice at this point, because we have a single function that is able to say what is going on inside the source, at the frontier, but also outside. So this is very nice with this kind of formulation, because we can take into account all the process inside the source, at the frontiers, and outside. So you have the formulation here. And what is appearing at this moment is you have now three contributions. You have a first one, which is a classical noise generated in the fluid volume, which was derived directly from the lattice tensor that you recognize involved here directly. It's a volumic contribution, so you have an integral in volume over the volume of the source region. Then you have two other contributions, which are only surface contributions, which correspond to dipole sources and monopole sources. That's what we are calling loading noise and thickness noise. I will try to explain these two names in a coming slide. But main idea at this point is to see that you have now different contributions that comes from these three terms: an integral in volume and two integral over surfaces. Another integral, in fact, to take into account the fact that you can have moving walls that will displace some air and that will create some fluctuation of the mass of air that is displaced over time. So let's have another view of these different noise sources that are taken into account in Fox-Williamson-Hawkins analogy. So we are going to consider to distinguish three contributions: thickness noise, loading noise, and volume noise. So thickness noise, monopole; loading noise, dipole; and volume noise, quadrupole. First one, imagine you have this drone, you're near the blades, one of the blade system of this drone, and you have the blades that are rotating. So the first obvious contribution is the fact that you have some air which is pushed by the blades during this rotating motion, and this air which is pushed is creating some noise, because you can have variation of the air which is pushed. If you change a regime of the blade, or even if you move along the radius of the blade, you see that you don't have the same velocity, and it fluctuates in time, this velocity of air. So this is called the thickness noise. Thickness because it's related directly to the thickness of the blade. The larger the blade, the larger the amount of air which is pushed. So this is the first contribution. It's a monopole source contribution. If you remember, when I talked about monopole contribution, I was talking about fluctuation of mass flow rate. So it is exactly the same contribution that is appearing here. So thickness noise, as you can imagine, for low Mach number flows, this is the most important contribution. This is the main contribution. And then you have a second contribution, which is called the loading noise. This is the interaction of this rotated air by the blades and the external air, which is due to the motion of the drone. Because the drone is moving into air, so air from the point of view of the blades, air has some velocity which is arriving on the blades, on the air pushed by the blades. So you have the interaction between the external air, which is arriving in the blades, and the air which is rotated by the motion of the blades. So this interaction with two contributions is typically a dipole source. So the air that flows around the blades will interact with the air that is rotated by the blades. This is the loading noise. And a third contribution, when the blades are rotating inside the air, they will create some turbulent flow wake behind them. And in this turbulent flow wake, you will have many kind of eddies that will interact between them. So this kind of friction between the eddies in the wake flow, this kind of frictions that will create some noise. It's a volume noise because all the eddies are evolving inside the volume around the blades and the air push. And so they will create some noise due to friction between these different eddies. The volume noise is a quadrupole source typically. It's a large spectrum of eddies that are creating behind the blades as they move, as they rotate, that will create this contribution. So this third contribution, it's a volume noise, and it's a quadrupole source. When I say quadrupole source, you must immediately think about a very low level of sound emitted for low Mach number flows. So we know that this contribution is very low, but it appears, it's there. It's a turbulence noise. So remember, when you consider Fox-Williamson-Hawkins, in the source region you have three contributions: thickness noise, due to the motion of the blade; loading noise, interaction of the motion of the air due to the blade rotating and the external air, due to the motion globally of the drone. And the volume noise, remember, due to the eddies that are created when the blades are pushing the air. Behind the blades, you have all these kind of eddies with different sizes that interact, that enter into interaction, and that will create some sound. So now that we have the acoustic analogy, we know that we are taking into account small aeroacoustic fluctuation, but we separate them from large aerodynamic fluctuations. So we have two distinct problems. So we have disparate length scale when we are at low Mach numbers. And it's not an issue, because we can consider Navier-Stokes equation even incompressible. So we can calculate turbulence with that, this incompressible Navier-Stokes equation, so we create some contribution. And the wave equation will determine long push waves analytically, further away from, in fact, from the source region. So the far field up to the receiver, we are going to consider the acoustic information up to this receiver using only a wave equation which is simplified. Remember, it's a homogeneous wave equation. So you don't have any dissipation or dispersion losses during transmission, because it's an analytical solver that will be used to propagate this acoustic information. Second point is that you don't have to include the receiver inside your computational domain. You can completely separate the CFD domain. The CFD domain must encompass the acoustic source, the near field, but further away from this source region, you can do a resolution of the propagation of these acoustic waves completely separately. So the computational domain is only for the source region and a little further away, because if you remember, I was talking about all these boundary conditions problems. So it's nice not to have the frontiers of the source region right at the frontiers of computational domain. You want to have some space to prevent some waves coming back to the source. It's much less expensive calculation than direct CAA. Why? Because you can restrict the source region to very small regions. So it's completely different from direct CAA, where you have to consider everything in the close field, in the near field, but you have to consider everything and be careful, because you are going to propagate everything up to the frontiers. And that means also that you can focus your CFD resources on the source region only, and then do some strong and the refinement of your mesh outside of the source region. This approach is also less sensitive to boundary conditions, and so non-reflective boundary conditions are not absolutely needed. It's a good practice still to consider this kind of non-reflecting boundary conditions at this point. But you have some limitations, as you can imagine, for the acoustic analogy approach. Main limitations is that externally, outside of source region, you won't have any reflection or scattering of these acoustic waves. They are propagated in a quiescent medium, no obstacle. You don't have any heterogeneities in the acoustic medium, which is carrying the acoustic waves. So if you have a hotspot inside your external medium, you are not going to represent the influence of this hotspot on these acoustic waves. You are completely going to ignore this contribution. So you need to be extremely careful with that. When you consider the external propagation of your acoustic waves, you are not going to take into account changes, strong changes in the acoustic medium properties. And as a consequence, you cannot consider backscatter, that is, the acoustic wave is propagating and changing locally the properties of the flow that it sees. So this kind of backscatter effect, you are going to completely ignore them. So no acoustic coupling inside the flow, no vortex shading triggered by acoustics, so no backscatter effects. So you won't have any effects of the flow on propagating, so on the transmission path. So you're not going to have standard reflection, partial layers or boundary layers. These effects are ignored. So that's why usually Fox-Williams and Hawking's acoustic analogy, you are not going to apply this approach in internal acoustics. That is, noise propagation in ducts or wall enclosed space. Why? Because you have reflections, you have complex acoustic effects, and the acoustic analogy is not designed. Remember the writing of the Green's function. you don't have any obstacle, you don't have any obstruction. It's a very simple function. It just says, oh yes, I see I have this source which is localized, I propagate it, and it's nice and easy. So another point, but I already talked about that, you cannot consider strong variation of the physical properties of the acoustic medium. So if you have a hotspot inside your acoustic medium, far away in fact from the source region, you're not going to consider the impact of this hotspot on the transmission of the acoustic waves. So you need to be careful as well. So that's all for the main ideas and rationale behind the acoustic analogy and the Fox-Williams rankings. Let's now see how it is implemented and used inside ANSYS Fluent. So the most general acoustic integral formulation, you remember I was talking about 3 contributions. Here you have thickness noise, which is recalled here, loading noise. You have different writings, which are detailed in fact in this reference, but main idea is here that you consider thickness noise and loading noise. Thickness noise, main contribution, loading noise, second contribution, and quadruple turbulence noise, I would say. On this distance are between the frontier of the source up to your receiver. And it can be a permeable integration surfaces that you have inside the source region. So I will talk about it a bit later, but you can consider the walls of your body, of your obstacle that is creating this sound, but you can also consider as source frontiers a permeable surface for integration of the source contributions on the frontiers of your source region. That is, you can have different kind of source contributing to the sound. You just need to be careful at some point, because if you count all these contributions, you can count the sound contribution twice. If you have a wall here and then a permeable integration surface here, you can count twice the sound between this region and this one. So you need to be careful at this point. Okay, for low Mach number flows, remember I was talking about that last session. Monopoles and dipoles are the dominant sources. So the quadrupole, in terms of contribution, it's clearly negligible compared to dipoles and monopoles, if dipoles or monopoles are present. It's not always the case, but usually you have dipoles and monopoles. So in the Fox-Williams rankings implementation in ANSYS Fluent, when you propagate the sound information from the frontiers of your source region up to the receiver, you are going to drop the quadrupole term. So you are going to consider only the thickness noise and the loading noise. Remember the ratio between this contribution evolves as the Mach number to a square. So for Mach inferior to 1, largely inferior to 1, this quadrupole contribution is much, much lower than 2 ones, monopole and dipole. Yes, I was talking about the frontiers that we consider inside ANSYS Fluent. You can consider solid walls. Obviously, you can consider the walls of your obstacle as a frontier, a source for your sound. It's an obvious choice. But you can also consider permeable integration surfaces. That is a surface that marks a frontier only for the source region. Not particularly for the CFD, the flow calculation. It's some sort of artificial frontier that you can input inside your domain to say, I want to take into account the contribution from the walls, but also the contribution from all the eddies that are creating inside this volume between the obstacle and this frontier, this artificial frontier. And then you can calculate, propagate the acoustic information from this frontier up to the receiver. So with quadrupole terms drop for low Mach numbers, when you consider solid source surfaces, you will not take into account in fact quadrupole noise. Why? Because when you are at the source, when you are at the walls, you don't have any turbulence, because at the walls, if your obstacle is steady, fixed, there is a thickness noise and the loading noise. Remember, the ratio between this contribution evolves as the Mach number to a square. So for Mach inferior to 1, largely inferior to 1, this quadrupole contribution is much, much lower than two ones, monopole and dipole. Yes, I was talking about the frontiers that we consider inside ANSYS Fluent. You can consider solid walls. Obviously, you can consider the walls of your obstacle as a frontier, a source for your sum. It's an obvious choice. But you can also consider permeable integration surfaces. That is a surface that marks a frontier only for the source region. Not particularly for the CFD, the flow calculation. It's some sort of artificial frontier that you can input inside your domain to say, I want to take into account the contribution from the wall, but also the contribution from all the eddies that are creating inside this volume between the obstacle and this frontier, this artificial frontier. And then you can propagate the acoustic information from this frontier up to the receiver. So, with quadrupole terms drop for low Mach numbers, when you consider solid source surfaces, you will not take into account, in fact, quadrupole noise. Why? Because when you are at the source, when you are at the walls, you don't have any turbulence, because at the walls, if your obstacle is steady, fixed, you don't have any motion. So the flow is at a null velocity around the obstacle, so you don't have any turbulence. So effectively, when you consider solid source surfaces, you won't have any quadrupole noise, because when you say quadrupole noise, you say turbulence, and when you consider the walls, you don't have any turbulence, so you don't have any quadrupole contributions. And you don't take into account, for example, solid vibrations. We are not modeling this, for example. So this kind of solid vibration could create some quadrupole noise contribution, but we are not going to take them into account. And you don't have any turbulence information, so you don't have any quadrupole noise information. When you consider permeable porous source surfaces, you have a quadrupole contribution inside the source surface, and you account for if you have the correct spatial and temporal resolution. I insist, you take into account this contribution only if you are sufficiently resolved in space and time. Remember, that's exactly what we saw on session 1 regarding direct CAA. Inside the source region, you have the same requirements as you have for direct CAA. That is, you don't want to dump all your acoustic information. You need to be extremely fine in terms of space and time discretization to capture this acoustic information inside the source region. So you need to be careful. Okay, you can get the quadrupole contribution, but you need to be sufficiently fine and fast in terms of representation of the time step. But when you are outside the source region, you will drop this quadrupole contribution. You will always ignore this contribution. You will not transport it up to the receiver. Okay. Inside the GUI, in the tree, you have acoustic models. If you check acoustic models, you will have access to this window, acoustic models. Then you can activate the Fox-Williamson-Hawkins, checking this option. And then here you have a specific option, convective effects. You can check it. When you check it, what's the purpose of this one? It's useful, in fact. It's an option that will take into account the fact that you have some global flow velocity around your source region. So imagine you have the source, then you propagate at the frontier of the source an acoustic wave information, but you have some wind, for example, some flow velocity that is affecting, in fact, the acoustic wave when it propagates from the source to the receiver. And in such situation, it will create some transformation, some modification of the acoustic wave information. And this kind of modification can be taken into account if you check this convective effects option and then specify the direction and the intensity of the string velocity that will affect the propagation of this acoustic wave. Here, for example, the user is checking this option, specifying the direction but not giving any intensity for the velocity that is pushing the acoustic wave. So here you don't have any effect. But if you say, for example, I have a wind of 5 meters per second, you input 5 here, this 5 meters per second will affect the sound that is perceived, that is captured at the receiver. Okay. So in ansys Fluent, when we consider the Fox-Williams knockings, we have different ways of using this Fox-Williams knockings utility. Main idea, just to show you in the first step. You do your calculation. So here the user is imagining that you are doing some SRS, scalar thermal simulation. So it can be LES, SDS, SBS, or SAS solution. You can do your hands, but it is usually less accurate than SRS, so that's why we point out SRS at this point. So with arbitrary surface motion, so you can do this kind of calculation. It's a transient calculation. The main idea here is to have a transient calculation. And when you say transient calculation, usually it's nice to say SRS calculation. So you have this calculation, which is done. And then you have two choices. First one is to do, in fact, calculate the receiver signals simultaneously, that is on the fly. So you will do a single calculation, and you will do SRS and the calculation on the fly of the source signals. So this is the same calculation. When you finish your SRS calculation, you will also have the information about the receiver signals, and that's all. Or you can store the information of the source surface data. You pursue your SRS calculation, but you are not computing the calculation of acoustic information up to the receiver. So you will finish your SRS calculation, you will have the source surface data, you export it during time integration, and then in a second step you will read again this source surface data inside Fluent, and then you will compute separately in the second step the acoustic propagation of the acoustic information, the frontiers of your source region. And then you will obtain results, that is spectra of pressure, of acoustic pressure at different receivers and so on. This model we will talk in more details in the oncoming presentation 4. Okay. So source data export method, that is the method on the left I was talking earlier. So you obtain your LES DS solution, you activate the Fox-Williams knockings acoustic models, you select export acoustic source data, you integrate your solution in time. That will create two kinds of files, index files and ASD files, ASD standing for acoustic source data files, and then after integrating you save your Fluent case. In a second step, it's over for step 1. So you have everything, but you have not recovered the signals at the receivers. You have everything to prepare the calculation, the analytical calculation of the propagation of the acoustic waves up to the receiver. In step 2, what you do is you read your Fluent case, you read the .index and .asd files, you specify the receiver locations in acoustic receiver panel, and then you write the acoustic signals in a separate step, in this step 2. So this is a different calculation, which is usually quite short compared to the CFD, classical CFD calculation. And then you will have some signals of acoustic pressure at the different receivers you specify. Remember, you can specify your receivers outside of the computational domain that you use for CFD. And then you post-process acoustic data. So how do we do this in the GUI? So we have the setup, the tree, the general tree. I was talking about models, acoustics. Here you see that you have Fox-Williams knockings. That is, we have this model activated. It's written that way. So you double click, you will have this window. Remember, you check this option, and then you will have corrective effects. I already saw that option, but we can define the sources and the receivers. So for the sources, so you click on that button, define sources, then you will have this window that will appear, and then you have important choices to make at this point. So the source zones Fluent by default will allow you to select walls, of course, but also permeable interior source surfaces. But if you do this for interior source surfaces, ANSYS Fluent will ask you to specify the inner cell zone, just to say what is going outside. Where do I consider what do you consider as inside source region and outside of source region? So it must be a marker between two different cell zones at this point. So you need to be careful at this point. And you can consider as well walls. Yes, important at that point. If source data is exported, you can consider redundant surfaces to be selected. That is, surfaces that are enclosed inside them. For example, here you have this configuration with this landing gear, which is going to create some sound, and you have a different set of surfaces that are considered. For example, the walls of the landing gear, but also three encompassing enclosing surfaces: Fox-Williams X1, 2, and 3. And all these surfaces are enclosing the other ones. That is, Fox-Williams 3 encompasses 2 and 1, and so on. So that means that when you do this kind of export of data, you can encompass multiple times the same volume. So you need to be careful at this point. And when you consider the export of the acoustic sources, you have also other considerations to take into account. For example, you have to specify a writing frequency for source data export and the number of time steps per file. So, for example, here a user is selecting 500 time steps per file with a writing frequency of 10, and here you have the name. One important point here is to consider the Nyquist frequency, which is a max frequency that you are going to recover. When you do your CFD calculation, you have a time step for the CFD calculation. So here, for example, is 2.5 microseconds. And this is a time step for CFD. And when you say 10 for the writing frequency of the acoustics, you are not considering this 2.5 microseconds, but 25 microseconds as a time step for the acoustic information. So that will change, in fact, the Nyquist frequency that you are going to obtain for the acoustics. So for example, for the CFD, with this value for the time step of the CFD, you have a Nyquist frequency, a maximum captured frequency, which is around 200 kilohertz. So it's quite high. Remember, the audible range of the human ear is up to 20 kilohertz. So saying 10 will decrease, in fact, this maximum frequency to 20 kilohertz. So that is this is a nice choice at this point, because when you consider the maximum frequency for the acoustics, you have only 20 kilohertz. It's nice for a human ear. So you have a safety margin here, but 20 kilohertz is a safe margin for human ear. So it's nice to see that this value is admissible for this kind of acoustic data. Okay, surfaces, they need to enclose dominant sources and important scattering surfaces. So you usually consider the walls as a potential source surfaces. It's a good practice, but you can usually also consider permeable source surfaces. So you have two choices of permeable source surfaces. First one is a small circle around your cylinder, which is your obstacle. It's creating, in fact, all the acoustic contributions. And you have a second choice, which is given here, which is this shape, which is much larger than the first circle, and that is enclosing a larger amount of eddies. So when you compare these two permeable source surfaces, the second one, the larger one, is going to consider more quadruple contribution from all these eddies. So usually it's a nicer choice if you want to take into account as well quadruple contributions. Okay. some guidelines to help you a little, because it's not always easy, in fact, to assess the influence of the positioning of the Fox-Williams unlocking surfaces. Here you have some guidelines for jet noise, with a reference on this point, giving you, in fact, some hints about the influence of the positioning, the location of these Fox-Williams unlocking surfaces. Here the authors are investigating different locations of surfaces around the jet. And here you have surfaces that are more or less enclosing the jet. When you consider, in fact, the larger set, which is this one with dashed line, you see that you have an impact, in fact, on the spectrum. At some point, some pressure level spectrum will have a cutoff at high frequency, because you have misplaced, in fact, the Fox-Williams unlocking surfaces, and you are damping some contribution from some eddies at the borders of your jet. So you need to be careful, because based on the location of the surfaces, you are going to recover some contributions, more or less. You need to be careful at this point. So regarding these surfaces, the authors are advising you, in fact, not to place the location of the surfaces too far from the borders of the jet, which means you have to define, in fact, a mean border and so on. Unless, if you don't do that, you will miss some contribution, and you will miss a small fast eddies contribution at this point. Another example here to help you is a fan noise. You consider a fan, you have an engine axis, you have the fan here, and you have some shroud around the blades. You have the hub here represented, the shroud of the fan, and you have the blades of the fan. First obvious choice is to take into account only the blades of the fan. It's an obvious choice, but problem is that you can expect only a limited accuracy. Why? Because you are going to take into account contribution from the surfaces of the blades, but not the direction of the eddies, for example, with the shroud, with the axis of the engine, and so on. So this is a first obvious choice, but it's not that accurate. Another choice would be to consider fan blades plus hub and shroud rolls. So it's much better at this point, and it allows you to distinguish, in fact, the contribution from the shroud, the hub, and the blades. And you have a third choice, which is given here, which is to consider permeable surfaces, which enclose, in fact, the hub, the shroud, and the blades. So you will take into account as well volumic sources and quadruple sources, in fact, corresponding to the eddies that you are capturing and representing inside the vicinity of the blade passage, or the blade passing and rotating. So it's very nice also to have this kind of choice for the enclosing surfaces. Yes, I was talking about that earlier. When you consider a permeable surface, either an interior or a sliding interface, which can be the case here, you see that if you consider a sliding mesh for the fan, you can consider sliding interfaces as source regions, source surfaces for the source region of the acoustics. You need to consider that they will take into account contribution from the walls as well, because you have the correct mesh to represent the propagation of the waves created at the walls. And if you have the correct mesh resolution, you will propagate sufficient acoustic information from the walls up to this frontier. So if you consider both sets of surfaces, and you take into account, when you calculate acoustic information, both sets, you will count twice the contribution from the walls, because you will have a first contribution directly from the walls as source surfaces, and the second one because you are having the contribution a second time at the borders, at the frontiers of the source, because you are propagating with a sufficiently fine mesh the contribution from the wall a second time. So if you consider both sets in a single calculation of the acoustics, be careful, because you are going to consider twice the contribution from the walls, for example. So a nice practice is to consider all these surfaces, but when you calculate the acoustic information, to calculate it separately. that is to make different calculation of the acoustic information to the receiver with different set of surfaces. It allows you to distinguish, in fact, the different contribution from all these surfaces. And it's very nice to see, oh yeah, I see that, for example, the hub is contributing to this percentage of the sound pressure level and the blades at this percentage and so on. So it allows you to distinguish the importance of each element of your fan, for example. So that's all for the source surfaces. Regarding the receivers, it's quite easy at this point. You specify the number of receivers and their locations. So if I go back to my window, yes, I was talking about defined sources. So I was inside this one, and you came back to this window, acoustic model window, and you click on define receivers, and then you will have this window where you will set the number of receivers and their location. Remember, the location of the receivers, it can be anywhere, that is, can be outside of the computational CFD domain. So here, for example, you have the landing gear, the source surfaces, and then you have the receiver, and some of them are clearly outside of the computational domain. So each receiver will generate, in fact, a signal file marked with an extension ARD for acoustic receiver data. You will specify the locations in these columns, and you do not need to be, they do not need to be specified if only source data is extracted. At this point, you can do this in a second step. But when you want to extract information and perform the acoustic calculation, then you need to define, in fact, the acoustic receivers. It's not compulsory in the first step if you separate, in fact, acoustic calculation, but when you do acoustic calculation, then you need to define the receivers to say, I want to propagate acoustic information up to this receiver and so on. Okay, now, how to save, in fact, the source data file. So first step is to prepare your CFD calculation, to run it. So you'd have to define the time step size, the number of time steps, to define the number of iteration per time step. And at this point, it's easy, you just have to calculate, and we create, in fact, the index file and the ASD file, the acoustic source data files. So the acoustic signals are created at the source data, at the source surfaces that are set, and now you want to perform, in fact, the acoustic calculation up to the receivers. So this is a second step. You read the acoustic source data files. You will have a set of potential source zones. Some can be active. So here, for example, the user is activating only the walls of the landing gear. You have a certain number of source data files. If you select only a certain set of this source data file, you will consider as only a portion of your calculation, a portion of the time steps that will be used to create, in fact, the contribution in terms of fluctuation of the acoustic pressure. So it can be only a portion of the total calculation you perform. Usually it's nice to consider everything, because when you consider everything, you will have a finer spectrum. You will have more information, then you can create a finer spectrum. And regarding the receivers, it's exactly the same idea. You can consider all receivers, but or only some of the receivers. Obviously, if you consider less receivers, the calculation will be much quicker, because you will have to propagate acoustic information from only one compared to 2, 3, or 4, or whatever. So the less receivers you have, the faster will be the calculation for the acoustic information. Okay, and when you have calculated all this contribution, you will be able to extract some information. For example, here, a contour of acoustic properties, you can extract surface DPDT, DRMS, even if we have better quantities now to extract information. But yes, at this point you can extract temporal derivative of acoustic pressure, and the RMS of this the temporal derivative is also accessible, available. Yes, at this point it will be only available for the selected active source surfaces. It's important. You won't have access to this quantity for other surfaces. Why? Because it's only available for the activated source surfaces. Yes, I was talking about the fact that you can select all or only a portion of the signal to recover the signals, the acoustic pressure signal at the receivers. And when you have this signal, in fact, you will ask yourself at this point, how long do I need to extract relevant data for the Fox-Williamson-Hawkins source? So here, for example, you have these acoustic pressure signals that is calculated, and you want to consider different portions of this signal to rebuild, in fact, the spectrum, the sound pressure level, in fact, in terms of frequency. And yes, you can consider shorter portion of the signal, but if you have shorter portion, you will have a cruder spectrum, a coarser spectrum. And here, for example, if you want to have a precise measure, an accurate measure, the maximum of SPL versus frequency, here you see that the frequency is completely wrong. It's completely missed. So you need to have at least a certain duration of the signal to obtain a fine spectrum. And the longer the duration of the signal you consider, the finer the spectrum. At certain point, it can be extremely fine, extremely difficult to read, and we will see some techniques to smooth this spectra. But usually, good point is to consider a long signal and then to smooth it in a second step, this signal. So here you have some considerations regarding the periods of the phenomena you want to take into account. For example, regarding the frequency of 700 Hz that we're going to consider, will give us a certain period, corresponding period. A nice guideline at this point is to consider at least 10 times this period of phenomenon when you consider the duration of your acoustic signal. And then you will have 10 times this period, which is appearing, and that will give you a nice appearance of this peak inside your spectrum. So, for example, it's some kind of guidelines that you can consider. So it says here at least 5, usually 10 is best. Yes, when you have several sources, problem is that you can have different sources, different locations of all these sources, and they can create different signals. So usually a good practice is to combine the signals received by all these source surfaces and say when the signal from this contribution is too short, I do not consider it, or I trim the signal. So this is done by default. It's called peer running, and you don't have to worry too much about this because it is done by default. All the source surfaces are taken into account properly, just to say I will take into account all sources on an equal state. So let's go through some case studies for the Fox-Williamson acoustic analogy. We see some applications, fan blades, propeller blades, plate wake, as well, cylinder wake, some jet configuration, and some words on the landing gear, if you remember, which is a more complex obstacle. So first case is fan noise. Very classical. You can use sliding mesh plus a series calculation, or you can do a DSRF calculation. You can handle with Fox-Williamson rotationally periodic boundaries and model a single blade only, obviously. Or you can move the fan blade as source surfaces. That's exactly what we saw previously. So here the choice is made to consider only the surfaces of the blade as source regions. Include duct and shroud surfaces to source zones if surfaces are acoustically important. It's a nice choice as well because you will be able to distinguish the contribution to the level of sound externally outside of this region, outside from the fan. So it can be a good practice as well. Here for blades, obviously 2000 rotation per minute, blade passing frequency, usually an important frequency to consider, 133 Hz. For turbulence model, we consider LES with sliding mesh, and here radius of 1 meter with variation of angle phi varying between 45, 60 and 75 degrees, that is more and more near 90 degrees to the axis of the fan engine. And then here what we recover the fundamental frequency, which corresponds to blade passing frequency, and some harmonics, as I was talking about earlier. So here what you recover is typically tonal noise. So you recover the fundamental frequency and then harmonics of this frequency. So it is typically tonal noise. Another important observation that you can make at this point is that when you increase the angle, you will recover lower values for the power spectral density. That means that the sound is most certainly less and less important as you increase this angle. 45, 60, 75, you see that you decrease the intensity of the PST. Another example of fan noise, 6 blades, 2000 rotation per minute, blade passing frequency is 200 Hz. Another model for FRS, SAS, called adaptive simulation. You have different domains, domains corresponding to the fan with a sliding mesh. You can consider at this point the interface between the sliding mesh and the static mesh on both parts of the fan as source surfaces. And considering these regions, we have a grid upstream of the fan, which is creating in fact some homogeneous flow conditions in front of the fan. Then you have the fan, the axis of the engine, and then you have the atmosphere. And all game here is to recover the proper levels of sound pressure level behind downstream of the fan. Here you have a view of the quality of the eddies that are recovered inside but also outside near the axis of the engine. And here we place some receiver and recover the sound pressure level at blade passing frequency in terms of decibel at points further downstream of the fan, and you see that the level is decreasing steadily. Case 3, noise into DC under wake flow. You have this cylinder, and then it is strange because I'm talking about 2D. So our acoustic problems 2D are tricky. Why? Because when you consider flow structures, they see other flow structures and they see other flow structure over a certain length, which is called a correlation length. A correlation length is a length over which an eddy, a structure, a vortex, sees another vortex. When you are above this value, that is, this eddy won't see anymore the influence of another eddy. But it's important, this length, because it can give you, in fact, the contribution of uncorrelated eddies. And when you have uncorrelated, that means that you have uncorrelated source region for aeroacoustics. So it is a very important notion for the aeroacoustics, and usually it's very difficult to say over which distance the eddies are uncorrelated, because you don't have this information. You are doing only 2D. So this is an input. This is an input in the window for the acoustics model. You can do Fox and so things, but you will have an additional input which corresponds to the source correlation length. And this is an important parameter because it will affect, in fact, the intensity of the sources. Because depending on the length, the source correlation length, you will consider more or less eddies to contribute to the total acoustic contribution from the wake flow. So here a small overview of the importance of this correlation length for this plate. So 2D LES. It's not that good to do this, but here the authors tried to do the LES with a very small time step of 1 microsecond. Experiment gives some pressure level of 92 decibel at a peak frequency of 3400 Hertz, and depending on the correction length, you see that you strongly change, in fact, the sound pressure level. Good agreement seems to be obtained with a correction length of 21 mm, which is a significant portion of the plates. When you increase this value well above the length of the plates, you see that you completely miss the value for the sound pressure level. So you need to be extremely careful. Too short a distance and you don't have the correct sound pressure level, and too long a distance you have too strong a contribution for sound pressure level. So it's very difficult to set this parameter. So need to be careful when you do 2D calculation for the aeroacoustics, because you will have at certain point to recover a 3D information, and to recover this 3D information is to set in fact a correction length. Fifth case, the jet noise, fully expanded jet with Mach number 0.9. Information here about the temperature and pressure for the jet. Non-reflecting boundary condition if initialized by RANS solution, which is the case here. You have a slow flow. U infinite is 0.67 meters per second. So remember, I was talking about convective effects. Here you have a jet which is inside the co-flow, so you will add this value of 0.67 meters per second in the convective effect. So remember, this is exactly the example of convective effect having some importance, because when you have this convective effect, it will affect, in fact, the propagation of these acoustic waves at the borders of the jet. For the far field and the outlet, we consider non-reflecting boundary condition, that is, non-reflecting boundary condition here up to the outlet. Microphones are placed at around 100 diameter of the orifice, jet orifice, and we consider different angles, polar angle varying from 20 to 160 degrees. CFD domain, you see that the microphones are much further away from the frontiers of the CFD domain. It's exactly it's always the same idea. It's an illustration that you can place your microphone, your receivers far away from the CFD domain frontiers borders. Reflected disturbances appear at co-flow inlet and far field. That's why we are using non-reflecting boundary conditions to limit these reflections. We know that we have the jet which is developing in an open atmosphere. We are placing these frontiers because we cannot have an infinite domain. We don't have the resources to have this infinite domain, but we want to have information through the Fox-Rams links, not affected by the reflection of any waves. And we add, if you remember, I was talking about this sponge layer, we add a sponge layer to further improve the damping of all this artificial reflection of waves at the frontiers. Here you have the trends for the overall sound pressure level for the different calculation experiment with black points, and then the curves for the different calculation, RANS in black and blue, addition of NRBC, non-reflecting boundary condition and nozzle outlet. For RANS it does not change many things, same as previous curve, but with sponge layer you see that you have a strong effect at higher angles for the overall sound pressure level. So this is not a weak influence for the sponge layer, it is a strong influence for the sponge layer. It will have an influence at a large angle. So be careful, you always remember that you can add some, you have some artificial means to recover some better damping of acoustic waves at the frontiers of your domain. For the landing gear, we recover the sound levels at different receivers. For all these receivers, we have of course an acoustic pressure signal, and for all these acoustic pressure signals, we recover some spectra, some pressure level versus frequency for the different receivers. And what we can see here is that it gives you in fact an idea of the directivity of the sound. And we see that where you are placed at 90 degrees compared to the main axis of the landing gear, you obtain the stronger sound levels, 98, 97 decibel compared to 93 decibel for all other directions. So it's clearly an information about the directivity of the sound based only on the placement, the location of these receivers. Okay, this is the conclusion for the acoustic analogy and the Fox-Williamson Hawkins. I would like you to remember that when you do Fox-Williamson Hawkins, you are separating acoustics from aerodynamics. You are saying, I will consider a source region where I solve in fact all the contribution for sound, and from these frontiers of the source region I will propagate with an analytical solver an acoustic information up to the receiver, and that means that the receiver can be placed outside of your CFD domain. When you do this approach, this acoustic analogy approach in ANSYS Fluent, you can consider obviously solid surfaces, but also permeable surfaces. Just remember one thing when you consider permeable surfaces: these permeable surfaces must separate two cell zones. Because when you set these permeable surfaces as frontiers for the source region, you must say what is inside and what is outside. Just to say, I'm going to propagate the acoustic wave in this direction. So this is an important information. Remember that if you have only an interior surface in a single cell zone, it will not work. So be careful. Good practice is usually to combine the Fox-Williamson Hawkins method with an accurate unsteady CFD approach, and that means usually to use SRS, scalar resolving simulation, to provide quantitative data on noise at receiver locations. Because when you do SRS, usually you correctly represent, if you have the correct mesh and time step, you correctly represent the eddies and the propagation of these eddies inside the computational domain. Yes, several cases were presented. It was including jet and fan noise, with some guidelines on the location of the source surfaces for both cases. Okay, we stop for this presentation. Do not hesitate if you have question. Let me check the chat window. Do not hesitate if you have question to the WebEx chat window, or after the presentation you can use ANSYS Learning and Facilities. I will switch to the next presentation, which is much shorter, just to give you an overview of the Goutin noise model. It's an extension, I would say, of the acoustic analogy and Fox-Williamson Hawkins model within ANSYS Fluent. So, what is the idea behind the Goutin noise? Just to give you some elements on this additional model. The main idea of the Goutin noise model is to use in fact the Fox-Williamson Hawkins, but not on an unsteady CFD calculation, but on a steady state simulation with a single rotating reference frame. And the idea here is to recover only tonal noise for rotating machinery. So we are going to drop some terms, we are going to make some drastic simplifications, and when we do this kind of simplification, we drop some kind of information from the acoustics. Here we drop the broadband noise contribution, for example. We are going to predict only tonal noise when we do this. So if you remember this, the formulation I chose to use for the Fox-Williamson Hawkins, and here we consider thickness noise and landing noise. We don't have the quadrupole noise, not much. Yes, fan noise. When you consider fan noise, you have discrete and broadband noise contribution globally. For monopole, you consider discrete contribution. For dipole, you have discrete and broadband. So blade thickness noise, blade loading noise, when you have dipole contribution, you have discrete and broadband noise contribution. And the quadrupole noise contribution is a broadband contribution only. So here we are going to consider steady rotating forces and that is only a discrete noise contribution coming from sickness and loading noise. So it's only a discrete contribution which is taken into account. And it's a steady flow that is going to feed the model. So it's a steady flow with only discrete contribution. When I say discrete conversion from the noise, it means tonal noise specifically. Yes, I was introducing, in fact, the two ways of computing the acoustic sources and the acoustic receiver signals. And for the Volkswagen QTT, I was mentioning the fan noise forgotten. Now we know this third way to compute, in fact, other contribution, discrete noise contribution for a fan. This is a good noise model. Here, the idea is not to do a transient SRS calculation, but to have a steady run solution with a rotating reference frame, and to calculate receiver signal using the Volkswagen Hawkins based on this steady run solution. And from this information, to read the acoustic source data and then compute receiver signals. But because it is a simplified acoustic source data set, we'll have simplified receiver signals that will allow us to recover only tonal noise contribution. Just a quick look here, for example, a steady loading noise of blades. You have a fan with two blades. Solver rotates the signal, not the geometry. We consider only thickness noise and loading noise, dipoles and monopoles, but only for discrete contribution. Steady state compared to transient for the two-bladed fan, we see that we miss some intensity compared to the experiment. This is why? It's because we lose, in fact, some broadband noise contribution. But globally, we recover some levels which are interestingly close to the experimental ones. Why? Because when you consider these frequencies, which correspond to tonal noise, usually it's a tonal noise which is the main contribution, and the broadband noise is much higher in terms of frequency, has much higher effect at high frequency. For the setup, Volkswagen Hawkins is still available for steady-state runs SRF calculation. We use fan blades as source surfaces, so it is exactly the same as before. We define the sources, we define the receivers, and we are going to use an internal revolution. They are going to move these source surfaces through the code as specified in the acoustic model panel, and we specify a number of time step per revolution and a number of revolution to rotate these blades, because we are not explicitly rotating these blades, but we are using this approach to introduce an artificial rotation of these blades. So we can use a single blade and use the SRF approach and then specify artificially in a second step the revolution that we want to make for this blade, and then compute the signal that is artificially comes from the revolution of these blades. Yes, another example, 4-bladed generic fan, 40 degree period segment, so we consider only this segment, 67 revolution of this blade, acoustic pressure signal is recovered. Clearly you see that this is not a common signal for acoustic pressure. Why? Because it is too smooth. You recover some specific frequency. It's not a very rich content for frequency here. We clearly see that we recover some tonal noise contribution. Play passing frequency 67 Hertz. Play passing frequency, number of rotation per minute multiplied by number of blades divided by 60. So this 67 Hertz as a characteristic frequency, and then placing all this microphone at a distance of 1 meter compared to the end of the fan axis, we recover this kind of information. Clearly we see once again receiver 1 to 6, one has a strong signal, and compared to 6, which has a signal which is kind of different. Okay, some pressure level, exactly the same information as previously. We recover different signals, different intensity of signal for the different receivers, and then here same information which is extracted for the different receivers. We see that we have different contribution for the different receivers. acoustic pressure signal here shows exactly the same frequency signal. It's the intensity of the acoustic pressure which is clearly different in all cases. Yes, regarding Coutin noise model is only focused on a steady loading noise of blades, so it will call a steady state RANS solution. It will add a Fox-Williamson-Hawkins modeling to the steady state RANS solution, and then it will allow you to compute thickness noise and loading noise, monopole and dipole contribution, but only discrete contribution of this noise. It's important to see that it's clearly limited to discrete contribution, tonal noise contribution. And you will post-process receiver signals on a converged steady state solution. So this in a two-step approach at this point. Okay, I think it's okay. Excellent. It's last slide. So at this point, I will stop the recording. Let me stop the recording.